In this video, we will be taking a look at something called sparse files. We will begin with a quick overview of what is a sparse file and spend some time on understanding how NTFS represents sparse files internally. We will then take a look at the UsnJrnl, which is an example of a sparse file used by Windows. We will then move ahead and discuss how sparse files can potentially cause disk space problems. Towards the end, we will answer the question, can sparse files be used maliciously? Let's begin now. Sparse files are basically files which are mostly made up of zeros. So why would you have a file that's mostly zeros? These files are actually common in applications where you provision space in the beginning and use it over a period of time. Couple of examples would be databases and virtual machines. Let's say you create a virtual machine with a 100 GB disk. Now, you're not going to use up all the space immediately. In this case, what you see here, the operating system and a few files have occupied around 23 GB and the rest of the 76 GB is free. In other words, this 76 GB is provisioned but not being used. So this virtual machine's disk file or its VMDK would be a perfect candidate for a sparse file where most of this 100 GB would be nothing but zeros, right? Now, any file system can store files which are mostly zeros. When you say a file system has support for sparse files, what you mean is that the file system is able to store a sparse file intelligently. That is, it does not allocate physical blocks on the disk to simply store these long runs of zeros. Now, let's move on and take a look at how NTFS provides sparse file support. To do this, I will mainly be using two tools, FSUtil, which is a Windows built-in tool, and Active Disk Editor. Let's begin by creating a 4 MB file. An easy way to do this is by using the FSUtil command. So I open up the command prompt and type fsutil file new silly.txt and give the size in hex as 4 MB. I'm calling it silly.txt because what this command will do is it will create a 4 MB file filled entirely with zeros. Now let's see how this file is allocated on the disk by viewing it in Active Disk Editor. I navigate to the file and then inspect its file record. To check this file's contents on disk, I go to the data attribute and select the data run. The data run will have pointers to clusters where the file's content is actually stored. We can see that this file has been allocated 1024 clusters and the actual data is available in this cluster number on the disk. I can simply click on this and on the right I see the file's data as represented in the disk. As we expected, this is just 1024 clusters of all null bytes. Now if you think about it, this allocation on the disk is wasteful because disk writes are costly in terms of performance. And you are spending time writing 1024 clusters with all zeros to the disk. Instead of doing this, you could have just had some kind of indicator in the data run to show that these clusters are sparse. In doing so, you can avoid writing zeros to the disk altogether, which is a performance gain. You will also notice performance gains with sparse files when you're doing searches. For example, if a file is sparse, then you can only search in the allocated ranges, that is clusters that have real data instead of simply going through 0-byte clusters. So these are the basic ideas behind having sparse file support in a file system. Now we will see how to convert this silly.txt into a sparse file. You can do it with the following command, fsutil sparse set flag silly.txt. As the command suggests, this will just set a couple of flags inside the file's attributes. We can actually view it in Active Disk Editor. So I open it up again and navigate to the file. Go to its standard info attribute and inside the file permissions section, there is a bit indicating whether the file is sparse. So here you can see the sparse bit is set to 1. Also, if you go to the data attribute, in the header, there is a flag to indicate sparseness. So this flag will also be set to 1. In terms of the file's contents, nothing changes. It still has 1024 clusters all allocated on the disk. We have declared silly.txt to be a sparse file, so we can actually do some sparse operations on it. What I will do is, So this is a 4 MB file. I will set the first 3 MB of this file as sparse. To do this, I will use the command fsutil sparse set range silly.text start at 0 and end at 3 MB. With this command, what I am telling NTFS is the first 3 MB of this file is just going to contain zeros. So you don't need to allocate the first 3 MB on the disk. After running this command, we can go back to the data attribute. And this time around, you will see some changes. You will observe that there are 2 data runs now. The first data run tells you that the file has 768 clusters and all these clusters are sparse, which means they don't exist on the disk. NTFS has made a note here by setting the sparse flag as yes. Each cluster is 4K bytes, so 768 clusters will be 3 MB. So this corresponds to what we requested in the fsutil command. Also, if you look at the second data run, which is for the remaining 1 MB, there are 256 clusters allocated. Because I only mentioned the first 3 MB to be sparse, the last 1 MB will be allocated on the disk, even though this 1 MB also has only 0 data in it. So that's another thing to note. NTFS will not validate your data. It will just do what you tell it. So if the first 3 MB of the file has some data in it, and I tell NTFS to mark it as sparse, it will faithfully do it. So the data that you had in that 3 MB will be lost, or in other words, it will be deallocated. Moving on, you can also query the allocation status of the sparse file by running fsutil sparse query range silly.text. The output of this command gives you the sections of the sparse file which actually have clusters allocated on the disk. In our case, you can see it's telling us that at an offset of 3 MB from the beginning of the file, there is 1 MB of data that is actually allocated on the disk. You can also view the properties of this file in Windows Explorer, and you will see that the file has a size of 4 MB, but its size on disk is only 1 MB. So when you say NTFS supports sparse files, this is what it means. If you can tell NTFS which portions of your file are going to be all zeros, then it will indicate this information in the file's data run instead of allocating clusters on the disk. Now let's look at a practical example where Windows uses sparse files. We will look at a file called the UsnJrnl. The UsnJrnl is a file maintained by NTFS to keep track of changes to files and directories in a volume. The UsnJrnl is a sparse file. Now getting to a more specific definition of a sparse file in NTFS is sparse if it has at least one data attribute which is sparse. So in this case, the UsnJrnl has 2 data attributes, $J and $max. Of these two, the $J attribute is a sparse attribute. Therefore, the containing file, which is the UsnJrnl, is a sparse file. Let's take a look at it in Active Disk Editor. The UsnJrnl is found inside the $extend directory. I go to the MFT record of this file, and inside the standard info attribute, in the file permissions, you can see the sparse bit is set. Also, you might notice that this file has 2 data attributes. The one that we want to see is the first data attribute, which is called $J. This is the attribute containing the actual USN records. Zooming into this attribute, we can see that $J has a number of data runs. Let's go to the first data run, and here we see that it has around 65,000 clusters that are sparse, meaning these clusters are full of zeros and have no allocation on disk. If you look up, you can see the size of the $J attribute is around 300 MB. So this 300 MB includes the unallocated as well as allocated clusters. Now we will take a look at this file using FTK Imager. So I open up FTK Imager, go to File and select Add All Attached Devices and navigate to the C drive root. And as expected, inside the $extend directory, we find the UsnJrnl. If I double click on this, we can see the $J attribute. When I select this attribute, below I can see FTK Imager showing me the entire content of this attribute, which includes the sparse or the zero filled clusters. Basically, FTK Imager has expanded these sparse clusters into buffers of zeros. I'm going to export this $j attribute as a file, and once this is done, you can see on the disk it has a size of around 300 MB. So this is the normal behavior of a sparse file when you try to copy or export them. It will come with all its 0-byte clusters loaded into the file. We will now try to extract the $j attribute of the UsnJrnl using a sparse-aware application. I'm going to use Eric Zimmerman's triage utility called Cape. So I open up the Cape GUI and select Use Target Options. I give the target sources as my C drive and target destination as my N drive. I uncheck the flush checkbox because I don't want to clean up my target destination. In the targets, I select $j and then click on Execute. So this will be fairly quick, and you can see the status message, skipping sparse data area in $j. In my target destination, we can see the $j file. However, in this case, the size of the $j attribute is only 32 MB as compared to 300 MB that we got when we exported it through FTK Imager. Now, I didn't show all this to bash FTK Imager, but just wanted to highlight the difference between using a generic application versus a sparse-aware application when dealing with sparse files. Now let's take a quick look on reading and writing to sparse files. Sparseness will be transparent to the end user or the application that is reading a sparse file. That is, when opening or reading a sparse file, NTFS will automatically return buffers of zeros in lieu of the sparse clusters. This is what we saw when we viewed the $j file in FTK Imager, right? And when you're writing to a sparse file, every time the program has to explicitly tell NTFS, hey, this is a sparse file, I'm writing data to it, and these portions of the file are 0. So if you open up a sparse file in Notepad and make changes to it, it will lose its sparseness and become like any normal file. This is so because Notepad is not sparse aware. Same goes for copying or moving a sparse file as well. Since sparse files need to be handled differently than normal files, the Windows API provides a few options for dealing with sparse files. As you can see here, you can use getVolumeInformation to check if a volume supports sparse files. And the device IO control function has a few options similar to what we saw with the fsutil command. So last couple of things. The first thing I wanted to mention is how sparse files can actually misrepresent space in a volume. Let's look at an example. So this volume is 100 MB in size. If I ask you how many 50 MB files can you create in this volume, you would say 1 or maybe 2, definitely not more than that, right? But if you're using sparse files, you can bypass the loss of sanity and do something else. I'll show you an example. So this is a simple Windows batch script. It will iteratively create 550 MB files and mark them as sparse. Let me run this script on my 100 MB volume. Now, when this script finishes running, you can see the volume is filled with 550 MB files. To fully exist, these files need more than 25 gigs of space, but I'm able to create them inside a 100 MB volume because I'm creating them as sparse files. Now if you check the space consumed by the volume, it is a bit surprising. So if 1 or 2 files expands to its intended capacity, then my volume gets full. So the moral of the story is sparse files complicate space management. If you are using the NTFS quotas feature, then the user who created these files has effectively consumed 25 gigs of space from their quota, even though they have not really stored anything, right? Lastly, let's move on to the question of, can sparse files be used maliciously? When checking for this, I found an interesting article written in 2016 by Matthew Weeks. There he mentions a simple anti-analysis trick you can use. Basically, you convert a small executable into a large sparse file. This will not impact the loading of the executable. However, if someone tries to copy or move the executable for analysis, then it gets bloated up. He has also given a working source code which is about 20-25 lines. I have taken this source code and compiled it into an exe, which is sparsemaker.exe. Full credits on this to Matthew Weeks. Going on to a demo, I have a simple Hello World program which is 47 KB in size. I'm going to use SparseMaker to bloat this program to 1 GB. So I just need to give SparseMaker the name of the program and the required size. Now my Hello World program has become 1 GB in size. I run this program and then use Process Hacker to check its memory consumption. I don't see anything unusual here. So it looks like the Windows loader maps the executable in memory in line with the information found in the PE header. So it's okay if your executable is 1 GB. If the PE header says it's 1 MB, then that is all will get allocated. Now, if I try to upload this file to VirusTotal, it fails because when uploading, the file expands to 1 GB. And VirusTotal currently allows only a maximum file size of 550 MB. So with all that, we come to the end of this video. In summary, we started with the definition of a sparse file and went ahead and used a bunch of fsutil commands to understand how sparse files work. Then we looked at the example of UsnJrnl and talked about some problems with sparse files like misrepresenting space. He ended up with an example of how an executable can potentially bloat itself up in order to prevent analysis. I hope that was useful in some way. Thanks for watching.